Or eventually, in SOI silicon and insulator, you might have capability of 250 degrees, and if you judiciously cool it, and somehow you could probably tap a 300 degrees area zone. If you operate on silicon carbide, we'll discuss tomorrow about that, you could go probably even at 500 under the same conditions. But they do not operate at 500. They are not implied to operate at 500 degrees. So this is at present time, all electronics is based on silicon technology. Recently, because of this requirement for high temperature, there have been companies working on silicon and insulator. We'll see what silicon insulator is. The same silicon, only that on standard electronics, the chip, it's built on a wafer that is about 600 micrometers thick. Whereas in silicon insulator, on the top of that wafer, I have an insulator that is a glass, silicon oxide, and over the glass I have a very thin silicon that could be 200 nanometers or so. And the electronics is on that very fine sheet of silicon. So this is the point for which this silicon on insulator is different as technology. Why? Why silicon doesn't operate? Mechanically, silicon it starts to weaken at about 900 degrees, mechanically. But at 250 degrees, the diffusion of the impurities with which we build the transistor, diodes, whatever, the active components, starts to be active and quite fast. In a half an hour, basically, one could, see a diffusion of 10 microns in the depth of the silicon. If we have a thick wafer, sure, this will go deep in the wafer and you lose the properties of the transistor that, doesn't exist anymore. Circuit is gone. Whereas on silicon on insulator, there is no room to go down. It's just silicon oxide, it's glass, right? Diffusion will start to go laterally, but this will go about 300 degrees. So this is how you build or get some more capability from more or less the same technology. Technology of silicon on insulator and silicon, simple silicon, it's absolutely the same. It's the same wafer, same plant, same, absolutely same. Just that, you get a little bit more capability on the sensors. Now, if one would double that capability with some micro electromechanical system sensors, that means what micro electromechanical system is a device that contains mechanical component, a sensor, electronics that is processing what the sensor is, and big advantage that this block is next to the sensor. No noise, no stray noise, nothing. And then eventually it's transforming the signal from analog to digital and sends only the digital signal out. That would be the idealistic approach for a sensor. So I just want to mention that there's a large variety of such sensors available on the market. With the sensor making, if you just are the user, you'll be surprised to see that big bulky sensors basically inside they have just a small chip of silicon. But they are large because the requirements are like that and they have to operate under specific conditions. So talking about MEMS-based sensors, they basically they are capable to fulfill the few requirements. They are small size and of course mass. It's good to have small mass in gas engines, of course. It's a big advantage to reduce the mass of the engine, right? Now, these sensors could be fully integrated on the measurement protocols, electronics, and even with mechanical components. It's easy to integrate them. Sure, it's for the engine, it's not so easy because of the environment, but they experience very low noise level because the electronics is close to the sensing, to the transducer. They have high accuracy. They could be built with very high accuracy, or there is also an advantage if you want to target a large bandwidth of measurement. You could have multiple sensors, and each one goes on its own range of measurement. And you could tap on each of them according to, to get a high accuracy of measurement. They have low power consumption. So another major advantage, recall the diagram of consumption, sure. Control of the engine is very little, more it's coffee making than entertainment system, but still lower power consumption helps in many situations. And it's also possible to embed in wireless communication. I say why? Oh, when we talk unmanned vehicles, air vehicles, that would be a big advantage to have this type of sensor, or in condition monitoring, in which the data is not critical, it's not for control purposes. Now, the sensor technologies that we will be discussing immediately are on temperature sensing, piezoresistive, piezoelectric. These are very classical and capacitive. And no, photosensitive detection, it's a little bit more, it's a newer technology. Inductive sensing, also quite old, inertial detection, quite old, but in a new box, completely new box, very small sensors. Vibration-based sensors, and basically magneto-optical sensing. We'll discuss about all these sensors. The applications will be a little bit variable on that. Temperature sensing, the first thing that has to be mentioned is thermocouple, the seatback effect, basically joining two pieces of this like material together, welding them. They will produce a voltage, a small voltage, when a gradient of temperature is applied between the end of the wires and the welding point. And this is specific characteristic for different type of materials. This type of sensors operate at various temperatures, usually 300-400 degrees, but they could go up to 1,700 degrees. Thermoresistors, they are much more accurate than the thermocouples, but they need a power supply. So seatback effect generates the voltage by itself. You don't need anything, you just have to measure the voltage. The range of measurement temperature, it's in the range of few degrees. We'll see that at the table immediately. Whereas thermoresistors could go so accurate with fraction of a degree. Infrared detection sensor or borometers, they are based on radiation and infrared. So the amount of infrared and the frequency, the bandwidth, indicates the temperature of the targeted element. They are not accurate. They are not within degrees. They are within tens of degrees. But for certain applications, they are good enough. They are unfortunately not good enough for the blade temperature in the turbine, for example. Color-based measurements, these are common in test rigs to detect what is the peak temperature for certain type of regime. And these paints basically are applied on a surface, and then according to the color at the end of the test, the peak temperature it's mapped somehow. Now, we have to make a difference between temperature measurement and principle of temperature for measurement. And this is why I'm giving you this example. This is the sensor of 7 pennies. You might know the story of analog devices. They did a producer, probably the largest producer of analog components. And by early 90s, they realized that they would be out of market with Intel and Motorola line on digital. And they had to think about something new, and they hit it good with this MEMS. They built basically a first accelerometer that was the first commercial success of MEMS. It was a big success. Now, what happens? One guy from the team, originally there were 6 guys, decided that he wants to split, and he built his own company. It's called MEMS IC, Integrated Circuits. And he has this idea. He works for very many years on that. Actually, he was a professor in Simon Fraser University. That's why I happen to know him. And what is the principle in here? The principle is the following. I have a heater, and I have an array of temperature sensors. Now, this heater is continuously heating slightly. It's not a big temperature, but it's heating a bubble of air. Now, when I move this left or right, the bubble will move and will remain inertial, on the position. The trend is to remain on the previous position. And this, thermal sensors will detect the time. The clock definitely will realize what is the speed. Differentiate that, you will go with the acceleration. It will tell you the acceleration and the direction, in two directions. So it's very, very good idea indeed. And all iPods, the instrument with that. iPhones, the same thing. This is a sensor. All toys are instrumented with that. Because again, the biggest deal the company made, because company is located in China, it's selling these chips for toys for kids. And that was the deal for 7 pennies a piece. So it's not expensive. No, we have to admit that's not very expensive as a sensor, right? Piezo-resistive sensor, what does it mean, piezo-resistive? We have a conductor. Now, if we stretch that conductor, okay, the resistance of that wire will change, right? And we measure that somehow. Now, how we do the thing, it's an example here. The sensing element is right on the silicon element that is seen here. We have a tube that if it's sealed, basically measure absolute pressure with respect to the pressure that is originally the sensor was sealed with. Otherwise, it's a differential sensor. And what we have in here is just a protective membrane to make sure that particles they don't hit this membrane that is extremely sensitive. We talk about a few microns, 2-3 microns in thickness. We talk about 200-300 microns in diameter. It's very sensitive. Any dust or something could break the membrane, so that's why it's necessary to seal it. Now you might say, okay, this is MEMS, a big advantage. This guy is not expensive. It's say $1 or even less. Packaging, that is expensive because one person or even a machine has to do it somehow. And then it's all this, metal packaging thing that goes all around that usually is done by a machine, sure, but, it's labor involved into that. So this is how the sensor becomes about $300 a piece, at least on the shelf. Unfortunately, this is what happens with such sensors. Piezoelectric, it's another principle. They are materials, specific materials, called them piezoelectric. They have a certain structure, they are hexagonal, and if they stretch, they release electrons. So basically, if we impact the piezoelectric material or it bend or whatever, this material will generate some electrons. I could collect those electrons in a capacitor and eventually do something with that. It's not a very, I should say, it's hard to generate energy on that. You have to accumulate lots of such impulses or pulses on the material to generate some current, because this is a charge-based phenomenon. It's not a current. Right? So, but this doesn't stop. This is probably you saw those gizmos on the kids' shoes. They have the light on the heel, and when they step, they make light or noise or whatever. They are powered by this type of devices. You could imagine they are not expensive if they put them in the shoes, right? This is motion sensor from Nike shoes, right? This is the analog device, yes, the XL. Sensor, this is a chip that is 2,500 microns by 2,500, 2.5 millimeters by 2.5 millimeters. And on this surface, one has the sensor. You see the extent of the sensor. Sensor is small, right? And all around is the electronics. We have the overload for the charge. We have modulator, demodulator. We have reference, self-test. We have preamplifier. We have all the electronics on the chip. It's built such that in one single run of the technology, you get everything on the chip. Basically, when you take it out, you just package and sell it, right?